Herstmonceux Castle, home of the Royal Greenwich Observatory and the headquarters of British astronomy. So this is a fitting place to begin our program about the most momentous quarter century in the whole history of astronomy. In 1957, when we began these Sky at Night programs, the move from Old Greenwich to Herstmonceux was barely completed. The great radio telescope at Jodrell Bank was only just coming into operation. But the most significant event of 1957 was the opening of the space age, when Russia launched the first artificial satellite, Sputnik 1. The Russians had taken the lead, but the Americans weren't far behind.
5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Apollo 11. And in July 1969, Neil Armstrong became the first man on the moon.
I'm going to step off the limb now.
He stepped out onto the bleak rocks of the Sea of Tranquility.
It's one small step for man, one giant leap for mankind.
By the time of Apollo 17, Commander Eugene Cernan was driving over the moon. His memory of that trip is as vivid as ever. For instance, what about navigation on the moon's surface?
We studied, due to a great deal of your work, of course, on the mapping of the moon, we studied the area we were going to land so well that I really believe I knew it, at least from the air, from above, as well as I know my own backyard. However, when you do get down among the rocks and you do get down among the mountains, you do have to refamiliarize yourself because things now start to look different. And navigation itself didn't bother us, but there's no trees, there's no roads, there's no houses, there's no telephone poles. So depth perception and distance is very difficult. You would look at something and instead of being a kilometer away, it might be 10 kilometers away. You had no way to tell how far you were going or how far you'd come. We knew the size of the lunar module, so we could always look back and see it and realize it was getting very small, but many times we went around, sort of around a corner and over the mountain, and we were out of sight of the lunar module.
So far, you're the last man on the moon. When do you think the next men will go there? Can you give any estimate?
When there is a purpose, when there is reason, when there is motivation to go back to the moon, to use it as a base to further explore the solar system or whatever, we will go back. Until that motivation comes from some source, it may be a long time. I believe we'll go to Mars too. Again, we'll need motivation. When the Viking spacecraft landed on Mars and a television camera scanned the surface, if there is a little green man with long ears looking back, that would have been motivation. We would have been on our way to Mars today if that kind of motivation occurred. It could be motivation from within or from without. We'll go back to the moon. When, I just can't tell you, but there'll be someone who will follow our steps to the moon.
Manned flight is only one facet of the space program. Unmanned probes to the planets have produced some of the most unexpected results. The control center is the Jet Propulsion Laboratory here at Pasadena in California. This is one of the most dramatic places in the world, even though it may not look it. It's the DSN, or Deep Space Network. It's here that we receive information from probes so far away that they make the moon look very parochial. And here that we receive those incredible pictures of the volcanoes of Io, the icy craters of Dione, and the complicated rings of Saturn. Marvels that only the space probes can show us. The DSN is manned 24 hours per day, and it has been for a great many years. Remember, the first successful planetary probe, Mariner 2, bypassed Venus as long ago as 1962.
Pass 3571. Item 1, NA. Item 2, command mod off. 0235.
It was here that the most dramatic of all space pictures were received. The Voyager probes recorded the quick spin of the great red spot on Jupiter, now known to be a whirling storm. There were the satellites of Jupiter, Callisto with its icy cratered surface, and Io with its red surface, sulfur volcanoes and crusted lava lakes. There may be a sea of liquid sulfur underneath. Io, we discovered, is just about the most lethal world in the solar system because it moves right inside Jupiter's deadly radiation zone. And beyond Jupiter, the voyagers bypassed Saturn, showing the glorious rings which have turned out to be grooved for reasons still not properly understood. Then there's Titan, Saturn's largest satellite, with its thick nitrogen atmosphere covering perhaps oceans of methane. And the icy satellites. Look at Mimas, with one huge crater reminding one of the Death Star in the film Star Wars. We also send probes to study the inner solar system. Mariner 2 was the first probe to Venus. Then Mariner 10 went past Venus to Mercury, where it recorded barren craters like those of the Moon. But Venus, so like the Earth in size and mass, is a curious world. All we can see from above is the top of a cloud layer. The orbiting Pioneer probe mapped Venus by radar, showing active volcanoes. The surface temperature is 900 degrees Fahrenheit. Venus may once have supported life, but it certainly can't do so now. The Russian probes, Veneras 13 and 14, landed there in March 1982, sending back pictures of a very gloomy scene under an orange sky. On Mars, at least, there still seemed a chance of life. Unmanned probes, such as Mariner 9 in 1971, showed craters, valleys, and huge volcanoes. Mount Olympus rises to 15 miles, 3 times as high as Everest. Then came the 2 Vikings, which made controlled landings. They sent back pictures of a red, rock-strewn landscape. Material was scooped up and analysed, but to the regret of most astronomers, the results showed no positive sign of life. The story of Mars is linked intimately with that of the Lowell Observatory. In fact, the road up to the observatory is called Mars Hill. The observatory was established in 1896 by one of astronomy's great characters, Percival Lowell, because he thought, correctly, that seeing conditions here would be excellent, despite the weather of the present moment. Lowell equipped his observatory with a 24-inch refracting telescope. It's an impressive instrument and still used for planetary research. One man who uses it regularly is Dr. Charles Capon. It really is a superb instrument, and it's of very high quality, is it not?
Yes, it is. It's one of the finest optical instruments in use in America today. And of course, being a refractor, why, it's well designed for planetary research. It gives good high contrast, and we can use very high powers with the telescope, which gives us large planetary images. And of course, then you have to have quality optics when you have high power.
I remember, it was February the 24th, 1980, when you and I were observing together with this telescope, when we discovered something rather interesting.
Oh yes, that was a very exciting night. In fact, I think it was a couple of nights that we were out observing, and we saw the north cap of Mars split in 2. And this is something that doesn't occur very frequently on Mars. And in fact, I had looked for it for nearly 20 years and never seen it there. Then all of a sudden, you and I were observing, why, there it appeared that one evening.
I remember that very well. We made drawings to compare them afterwards, and they were pretty well identical.
Yes, and the photographs I took that evening also showed this rift in the cap.
The Lowell refractor is ideal for studying the planets, which are nearby and bright. But for more distant objects, you need to collect as much light as possible. The Mount Wilson 100-inch reflector, completed in 1917, has about 4 times the diameter but collects 16 times as much light. And in the 1930s, a 200-inch mirror with a far greater light grasp was planned for nearby Palomar. The problems of handling glass for a 14.5-ton mirror were formidable. After a good many trials and tribulations, the mirror was eventually cast. It took months to cool and many months more to grind the mirror to the correct curve. Inaugurated in 1948, the 200-inch at Palomar is still the biggest optical telescope successfully operating to this day. Admittedly, the Russians have built an even bigger one, but they haven't really solved all the problems about making a telescope as large as this, and further work is being done on it. Perhaps the way ahead lies with this, the multiple mirror telescope on Mount Hopkins in Arizona, built in 1979. It has not one, but 6 primary mirrors, each 72 inches in diameter, working together, which are equal in light grasp to a single 176-inch mirror. You may ask, why build a telescope as complicated as this? Well, there are 2 main reasons. First, making 6 72-inch mirrors is a great deal easier than making a single 176-inch mirror. And secondly, there's the question of cost. The MMT has cost only about 1/3 the price of our equivalent telescope in comparable aperture. If you think that the MMT looks unlike a telescope, then what about this one? It's the Solar Telescope at Kitt Peak, also in Arizona. The main body of the telescope doesn't have to move. The sun's light is reflected down the length of the tunnel and halfway back up again to produce an image in the laboratory. This is the tallest solar telescope in the world, as well as the biggest. The heliostat, that's the top mirror, is 80 inches across, and that's large by any standards. The function of the heliostat is to direct the sunlight down the tunnel, and it's a long, long way. Now I'm inside the main tunnel, traveling down in a kind of a cable car, which, believe me, is a lot easier than using the 100 or more steps. You may ask why this telescope has to be so large. Well, the main reason is that the observers want a really big solar image, and for this they want a large aperture and a long focal length. And of course, if they put the tunnel straight up into the air, it would be even higher than it actually is, and very much more difficult to handle. So this is really the best design. This is Halfway House. Remember what's happened. The sunlight has struck the big mirror at the top of the tunnel and is reflected downwards onto the mirror at the bottom of the tunnel. It's then sent back up the tunnel onto this mirror, which is absolutely flat. And that directs the sunlight downwards, again in a constant direction, through a hole in the floor, into the laboratory below, where the main analysis is done. The sun is only 93 million miles away, and you might imagine that by now we'd learnt all about it. Well, I can assure you we haven't. Of course, we have found out a great deal. We know that the sun is producing its energy by what are known as nuclear reactions. Hydrogen is being converted into helium, the sun is radiating and is losing mass at the rate of 4 million tons a second, and the central temperature is of the order of 14 million degrees. And ever since the early 17th century, we've studied the dark patches or sunspots. But recently, it's become clear that our knowledge of the sun is very far from complete. The latest discoveries have thrown new light on the nature of our nearest star. And to make these discoveries, solar astronomers now set up their experiments in the most unlikely places. This is the strangest of them all, Homestake Mine near Deadwood Gulch in South Dakota, land of the gunslingers of a century ago, Wild Bill Hickok, Calamity Jane, Dr. Holliday and the rest. Gold has been mined here ever since 1877. But gold isn't what the astronomers are after. 1 mile underground, the mine provides a convenient hole for the astronomers to set up their observatory. For it's not the sun's light they're after, but some elusive solar particles. It seems a curious place to study the sun. Just why are you hiding so far underground?
Well, we try to observe neutrinos. They produce a very small signal, and cosmic rays and many other nuclear particles produce the same signal we're looking for. So we have to come way underground and screen ourselves from cosmic rays.
Do you get any cosmic rays down here?
Yeah, there are few. Now, the number of cosmic rays passing through a square meter is kind of one every quarter of a day, something like that.
Which is not very much.
No.
Well, a neutrino with no mass and no charge is very difficult to detect. How do you trap it?
Well, a neutrino is very penetrating, and it goes right through the Earth, and we try to trap it in chlorine. It's captured by a chlorine atom to produce a radioactive argon atom. And we try to observe these few radioactive argon atoms that are produced.
And of course you have your chlorine in a large tank of cleaning fluid.
Yes, we have a very large tank. It holds 100,000 gallons of a chemical compound called perchloroethylene. It's a common dry cleaning solvent. So we have 100,000 gallons of that as a detector.
And what do the neutrinos do to it?
Well, they convert a chlorine atom into a radioactive argon atom. So in that tank, it produces one of these atoms every 2 days. And we have to remove that and observe its radioactivity.
And so, in fact, by noting the numbers of these particular atoms produced, you know how many neutrinos have hit.
That's right, exactly.
Well, what are the results to date?
Well, the results today are that we're observing too few neutrinos, roughly a factor of 4 below theoretical expectation.
Why is that?
Well, we don't know. We've known for about 10 years that we're seeing a low signal, and there have been many explanations suggested. Essentially, you can say that the central regions of the sun are probably not as hot as we think they are.
Ray, why is this experiment so important?
Well, because the sun is the closest star to us, and we know a lot about the sun. And to try to satisfactorily understand how the sun operates, how it generates energy, that tells us about the life and death of all stars.
Neutrinos may be difficult to catch, but so, of course, is the light from the faintest and most distant stars and star systems. Astronomers need to make the most of what little light there is. An electronic device to help them do just that was developed by a team led by Professor Alec Boxenberg, now director of the Royal Greenwich Observatory at Herstmonceux in Sussex.
Well, very basically, the idea is to look at single photons, which are the particles of light, of which light is made up. One can't be more sensitive than that. And the way it does it is first to intensify or to amplify the very faint image that we get in astronomy by a very large factor, something like 10 or maybe 100 million. And when you do that, you find the single photons, which you normally can't appreciate when one looks at something by eye, but they show up as splashes of light, independent splashes of light. And the detector observes each splash of light with a television camera, and then this is fed into a computer. And gradually, the very faint image builds up in the computer, and we can see it on a television screen, just as if it were a photograph in the end. Of course, it might take hours or even days to build this picture up.
Even with the help of electronics, optical astronomers need clear skies. La Palma, in the Canary Islands, is ideal and has been chosen by Britain and other European countries as a site for a new observatory. The INT, or Isaac Newton Telescope, has already been moved here from Herstmonceux. And here's the new dome of the INT, almost at the highest point of La Palma, at over 7,000 feet, with most of the clouds below us. As an observing site, it's superb, and incidentally, scenically magnificent. Inside the dome is the INT itself, expected to be fully operational by mid-1983. It won't be the only British telescope at La Palma. Work has already started on the site for a new 1-meter telescope due for completion late in 1983. And there are plans for another, twice the size of the INT. The 4.2-meter William Herschel telescope will be one of the largest in the world and will provide British astronomers with great opportunities. The project scientist at La Palma is Dr. Paul Murdin.
The main research is going to be research which exploits the fantastic site that we're standing at. The site is very dark, very clear. It has very good seeing, and it'll see very, very faint things very far away. I think the main thrust of the work, which will be done by British astronomers at the site, particularly with the 4.2-meter telescope, will be cosmological. We will penetrate further and further in look back to the start of the universe and penetrate cosmological problems.
Well, with a very large telescope here, under pretty ideal conditions, I think we may expect some fairly spectacular advances.
I'm sure that's true. You can't possibly be an astronomer now with a telescope like this at a site like this and not make fantastic discoveries.
Splendid though La Palma is, it can hardly rival the magnificence of Hawaii. Here we have the extinct volcano of Mauna Kea, rising to nearly 14,000 feet above sea level. The air is thin, and you have to be very careful not to move around too quickly. But here, Above 40% of the Earth's atmosphere, seeing conditions are superb, and 4 major telescopes have been set up. There's the 150-inch UKIRT, United Kingdom Infrared Telescope. Then there's the 88-inch reflector, operated by the University of Hawaii. Then the giant 144-inch Canada-France-Hawaii, or CFH telescope. And there's also a 120-inch infrared telescope operated by NASA. It's an impressive array. And yet one can hardly say that the site is accessible. For one thing, it's a long, rough ride from Hilo, the largest town on the island, and also it's very, very high. You have to stop for a while to acclimatize at the halfway house, Halepahaku, before starting the final half-hour drive up the very steep, rough track to the summit. Astronomers come here from all over the world, and every time they use the telescope, they have to make this trek, as it's considered dangerous to sleep at 14,000 feet, where the air is so thin. But this makes the site ideal for infrared studies, and much of the research here is devoted to it. Dr. Dale Cruikshank has been using the 88-inch University of Hawaii telescope for his own infrared studies of the solar system.
That's right. My colleagues and I have been using this telescope from its vantage point high in the sky to explore the solar system both outward from the sun and in toward the sun.
What are the main results so far?
We've found exciting things about volcanoes on Io, the most interesting satellite of Jupiter. We've found that asteroids are an enormous range of objects in terms of their surface compositions, and a wide variety of other things about the small and large objects in our neighborhood.
Dale, what do you see as the future of infrared astronomy in the solar system?
From vantage points such as this, there's a tremendous amount that we can do over the next several decades. Using the preliminary results given to us by spacecraft, we now can explore what's going on in the solar system in great detail, and we look forward to an enormous range of exciting topics and discoveries over the next many years to come.
And lastly, you've been using the 88-inch. Are you going to use the UKIRT for this kind of research?
Oh yes, the UKIRT telescope is a superb instrument for work in the kind of area that I study, and I'm confident that it'll continue to give me exciting results.
What's so special about the UKIRT? It's turned out to be just as good as an ordinary telescope, but because it was built for work in the infrared, the mirror didn't have to be so rigid, and the optical design was less critical. Alan Pickup explains.
Well, the principal difference is that the mirror is a lightweight mirror. A telescope of this aperture, 3.8 meters, would normally have a mirror of about 15 tons weight. UKIRT's mirror is only 6.5 tons, and this makes the whole structure of the telescope much lighter and cheaper to build.
There's a wonderful system known as chopping, isn't there? Can you tell us a bit about that?
Yes, we like to separate out the infrared signal from the star from the infrared signal of the sky. Of course, the sky is giving out infrared waves as well as a star or galaxy, whatever we're looking at. So we do this by looking at 2 small adjacent areas of sky. In one of these areas of sky, we place the star. In the nearby area of sky, we just have the sky. By subtracting the 2 signals we receive from each of these areas, we can examine just the signal from the star. And we do this by tilting the small secondary mirror of the telescope at the top of the telescope. By tilting this, we can effectively alter the pointing direction of the main telescope about 10 times every second. And this enables us to do this chopping between one position and another.
But Hawaii is still north of the equator. We need major observatories in the southern hemisphere as well. This is a peaceful place in the Warrumbungle Mountains in the heart of New South Wales. It's a timeless place where kangaroos and koalas roam at night, and it seems hardly to have altered since these volcanoes were finally quietened 13 million years ago. But this is Siding Spring Mountain, the home of one of the most sophisticated pieces of modern engineering. This is the dome of the Anglo-Australian Telescope, or AAT. It dominates the scene. It's 150 feet high, and it and the telescope weigh over 7,000 tons. Fortunately, it's built on firm foundations. These ancient volcanoes are very solid indeed. One's used to thinking of observatories perched on the tops of mountains. Well, there are no really high mountains in Australia, but Siding Spring, at well over 4,000 feet, is quite lofty, and conditions here are good. The decision to site a major telescope here was made in the 1960s, though it wasn't until 1975 that the AAT came into full operation. The mirror is 153 inches across and is generally regarded as the finest ever made. The telescope itself is fairly conventional. but it has one of the most sophisticated control rooms. Using the most up-to-date techniques, the telescope can be guided from here. The observer seldom needs to go near the actual telescope at all. Most observations are made electronically, and the results displayed and analyzed in complete comfort. It's true that during the last 10 years, astronomy has gone through an electronic revolution. Just as, long ago, the photographic plate replaced the human eye for most branches of research, so the plate is itself being superseded by electronic detectors for most purposes, but not all. There are some branches of research in which photography still reigns supreme and probably always will. And for photographic work, the AAT is ideal. One man who's taken full advantage of this and has developed new techniques which are proving to be of immense value is David Malin. David, how does photographing with the AAT differ from photographing with an ordinary telescope?
Oh, in several ways. I think the best thing I can do is to demonstrate, first of all, the size of the photographic plate we have to use. This is a typical plate used on the AAT, 10 inches square, much larger than any other normal format. The second major difference is the fact that our exposure times are extremely long, typically 60 minutes, sometimes longer.
Can astronomical photography still produce really valuable scientific results?
I guess it's still very important. You've mentioned previously, I think, the electronic revolution, which has come to pass in astronomy in the last 10 years. But photography is still absolutely vital for many branches of astronomy, mainly because we get an enormous area of information in one exposure.
What about colour photography?
Well, colour photography can be done. Colour film used to be used some years ago, but now we've found that taking 3 black and white plates through colour separation filters is the way ahead, and we're able to make colour pictures of extremely faint objects that way.
David, these are magnificent colour pictures. Let's begin with the Orion Nebula.
Yes, it forms the very famous shape of the Horsehead, which is a dark cloud of dust spreading into the bright nebulosity of the Horsehead itself.
These colours are really striking. Are they genuine colours?
They are representative colours, I think, is the best way to describe them. We've taken considerable pains to balance the 3 colours, the red, green and blue, in the photographs. But these objects are emission line objects. They're not like objects that you normally photograph with your everyday camera. They are composed of discrete lines of emission. And to balance photographs with line emission is very difficult indeed, but we think we're well on the way towards doing that.
I ask that because so many people think, having seen these magnificent pictures, you can actually look through the eye end of a telescope to see the colours, and of course you can't.
Unfortunately, that's not true. Even with a large telescope, the light levels are so low that the eye is working in its mode where it doesn't record any colour at all.
And here we have a very delicate one, the Filamentary Nebula, which contains the Vela Pulsar, a supernova remnant.
This is an extremely low surface brightness, a very faint object, never been recorded in colour before, and it's the remnant of the Vela supernova, which exploded, some 10,000 years ago.
And now, going out beyond our own Milky Way, we come to the spiral galaxies, and that is a magnificent picture of a spiral galaxy.
If we could get outside our own galaxy and look back into it, that's pretty much what you might expect to see. An object with old, mature yellow stars in the middle, bluish spiral arms, and along the spiral arms dotted the red H2 regions, like Orion, that you can see along the spiral arms here.
And now we come to this very interesting point of rings round elliptical galaxies, and I gather these have been discovered by you using your new techniques.
Yes, this picture was taken with the UK Schmidt. But the plates were massaged by techniques I've developed here, and in doing so you are able to see some very faint shells. Here is one such. We call them shells because of their luminosity profile. Shells around these apparently quite normal galaxies. And the existence of these is rather puzzling, but we're working on it to find out exactly what they are and to come up with some kind of model which would explain their existence.
That, I think, is one very striking demonstration that photography, and I mean photography, not electronics, is still very much a major force in modern astronomy.
Oh, it's still very important. We've heard previously that electronics is taking over from photography, but in fact the 2 techniques are complementary. Photography is still capable of making significant new discoveries, and it does so regularly, especially with the fine plates taken on this telescope and on the UK Schmidt.
I don't think anyone will doubt that these photographs are the best deep sky pictures ever obtained. But today, photography and electronics are complementary. Dr. David Allen has been at Siding Spring for 7 years, and he knows every aspect of the AAT. Of course, with this telescope, you did identify the Vela pulsar, which I think is I believe is the faintest single object ever recorded. Am I right?
It's the faintest star ever studied. This is one of the things that the radio astronomers find that's going bleep, bleep, bleep every, it's 11 times a second, I think. And previously only the Crab Nebula, the pulsar inside the Crab Nebula, was known to flash in the visible, whereas there are hundreds of these things flashing around in the radio sky. And people thought they ought to have a look for more optical ones. And it was apparent that they needed to be young. So the youngest was the Vela, which is only accessible in the southern hemisphere. It's a few years now since the measurement was made, but we managed to detect it. We saw the thing flashing on and off. In fact, it flashes slightly differently in the optical from what it does in the radio. It's telling us something about how pulsars work, and it seems to say that as they get older, the light they put out is falling very fast. In fact, so fast that I suspect if we'd been a century or two later in looking for this thing, we just wouldn't have seen it. It would have faded out completely.
Optical astronomy has developed in a way that was quite unforeseen 25 years ago when the sky at night started. Another branch of astronomy, in its infancy then, needs a very different kind of telescope, radio astronomy. And this is the world's most famous radio telescope, the 250-foot dish at Jodrell Bank in Cheshire. It's a colossal structure, capable of picking up radio waves from objects so remote that their signals take thousands of millions of years to reach us. And it's not only the world's most famous radio telescope, it was also the first really large instrument of its kind. It was set up because of the skill and persistence of one man, Professor Sir Bernard Lovell. There were plenty of problems to be overcome, not all of them scientific.
But we still had to find the money. I mean, by that time, the bill for the telescope, for which I had only got $250,000, had gone up to £680,000. We collected £100,000 fairly quickly, and then we were stuck for the remaining £50,000 or £60,000. By this time, it was 1960, and we were part of the ground network of the American space effort. We had come to this arrangement with great secrecy with what was then the United States Air Force. And Pioneer 5, the first series of Pioneer 5s, we had the job of actually not tracking it, but actually commanding it from this telescope. We sent out transmitted signals, which about 20 minutes after it was launched from Cape Kennedy, we released the space probe from its carrier rocket. And of course, this was all over the newspapers, front page news. The next day, the telephone rang, and the other end, the man said, "Oh, is that Lovell?" "Yes." "My name is Plingerley. I'm Lord Nuffield's secretary. His lordship wishes to speak to you." So Lord Nuffield came on the phone. "Is that Lovell?" "Yes, my lord." "How much money is owing on that telescope of yours?" "Oh, I think about 50,000. Is that all? I'll send you a check."
So that was a relief. After the strange and incredibly powerful quasars, or QSOs, were identified in 1963, they were intensively studied from Jodrell Bank. Sir Bernard retired as director at the end of October 1981, the end of an era. But he's been succeeded by another great radio astronomer, Professor Graham Smith. Graham, what about the quasars? What are the latest developments?
Well, I think that's the main bulk of work here. Of course, you know that the telescopes are used in collaboration with others to produce maps of quasars. And this is the most exciting thing because we can produce very accurate maps. And we find that quasars have got a very complicated structure. There are some very strange physical things going on in there. They're storehouses of energy, and they're producing radiation at a fantastic rate in little hot spots at the centers and far out from the center.
What do you think a quasar is?
It's got a certain sort of powerhouse in the center which we don't understand. Probably a black hole, but everybody says probably a black hole because they don't know where the energy is coming from. It could be a rotating black hole. That's the most likely recent theory.
Quasars weren't actually discovered here, and in fact the first positive quasar identification came from the Parkes Radio Astronomy Observatory in New South Wales.
It was an object
which was known to be a radio source, that is a source of radio radiation, to be an extremely small source. It had very little size, and the identification was made, funnily enough, by using the moon. As the moon slowly passed across the source, the radiation was cut off, and by knowing the precise time at which the moon cut across the object, we were able to get an accurate position. And this led, on comparison with an optical plate, to a identification with this object, 3C273, the first quasar.
And of course, when 3C273 was examined optically, I think it was at Palomar, then astronomers there, well, they had a considerable shock.
Oh, a very considerable shock. The spectrum was unlike that of any known star, and at that time it was thought that the objects were in fact stars. In fact, they were called radio stars. We now know, of course, that they were like no known stars. They were objects way across the universe, in fact, near the distant edges of the universe.
We're used to talking about redshifts in optical terms, but you can do the same kind of thing with a radio telescope. Are we absolutely certain now that these redshifts really do indicate these immense distances?
90% of people think so.
What do you think?
No. I think, let me put it this way, on Monday, Tuesday and Wednesday, I think they are indicative of distance. But perhaps on Thursday and Friday, they're not. There is, I think, a growing body of evidence that favours the fact that the redshifts are not cosmological, as we say. That is, that they indicate enormous distances for the QSOs. A particularly exciting recent bit of work done in the States was on the object I referred to right at the beginning, 3C273, when it was shown that two radio sources in 3C273 are moving apart at a very high speed. In fact, if 3C273 is at the distance we really think it's at, as determined by the redshift, then these objects are moving apart at 10 times the speed of light.
Well, that's surely impossible.
That is impossible on conventional physics, and if 3C273 is at its correct distance, and if there's nothing wrong with the radio observations. One of those three things is wrong. I would very much like to know which it is.
Professor Sir Fred Hoyle has no doubts at all.
Well, I don't believe the usual theory that their redshifts are indicative of their distance. I think that's nonsense, and I think there's overwhelming evidence to show that it's nonsense.
What evidence is that?
Well, there are far too many quasars found in clusters, and there are also cases now known of triplets of quasars which are in line with each other, the three of a triplet, to within the accuracy that one can determine by measurements on the best telescopes, which is to say, well within a second of arc. And such geometrical arrangements, they're not entirely impossible, but exceedingly unlikely. So I think this notion that the quasar redshifts are indicative of cosmological distances is just wrong. I mean, it's obviously wrong.
Well, in your view, how far away are the quasars?
I don't know how far away they are. I think they're comparatively close, and I think they are huge aggregations of mass.
In our galaxy or beyond?
Oh, beyond. Maybe 100 million light years, that sort of distance.
How does Professor Graham Smith view this argument?
Oh, that's dying down. I mean, that of course, has come and gone during this 25 years, and I don't think there's really very much fight left in it. They are indeed distant objects. They are indeed objects which are giving us information about the history of the universe, as well as about themselves.
When you say distant object, do you mean thousands of millions of light years further away than most galaxies?
Oh, yes. The most distant objects available in the universe are these quasars and the radio galaxies.
So we have two completely opposite theories, each supported by eminent astronomers. Quasars have certainly caused arguments. But during a quasar research program at Cambridge, using a peculiar-looking aerial array covering over 4 acres, a team led by Professor Anthony Hewish made an unexpected discovery, more or less by accident.
We were making observations of quasars and watching them as clouds of gas blew from the sun across the quasar. This gives you a flickering signal which we can use to actually measure the sizes of these objects. And that's an important measurement. So the telescope was designed to see this effect, plasma clouds passing quasar sources. And when the pulsar came, we obtained the flickering signal, which looked exactly like this effect. But normally one only sees this during the hours of daylight, because the line of sight then is reasonably close to the sun. Well, we were making a routine survey and the records were being carefully analysed by Jocelyn Bell, and she saw a signal which we first thought was the fluctuation we were looking for, but it happened at the wrong time of day. We were looking at every inch of the record, and she found this thing in the middle of the night rather than the middle of the day, and she pointed my attention to it, and we decided that since we were doing repeated measurements, it would come up again if it was a genuine signal, and that's how we got onto it. It came up once in a while, and so we then made a detailed investigation and found these very regular pulses, much to everybody's astonishment.
What did you think it was?
I thought to begin with it was probably radio interference. It just looked so totally artificial. But the detailed follow-up work showed that it couldn't be that. It was coming from a particular point in the sky that actually maintained its position quite accurately. And that pointed us to a celestial source, a genuine astronomical phenomenon.
This was the first pulsar, in fact.
The very first pulsar.
A very recent discovery has been that of the first pulsar beyond our galaxy, in the Large Magellanic Cloud, more than 150,000 light-years away. That discovery couldn't be made from Cambridge because the cloud is too far south in the sky. It was made from Parkes by Dr. John Abels.
You understand that pulsars are galactic objects. They're the result of the death of certain kinds of stars. Actually, the big ones, the ones that live fast, die young, and leave fascinating corpses. And this is the first time we've ever found a pulsar outside our own galaxy, and it's been done with this telescope and my colleagues from the university in Tasmania.
How exactly did you locate this pulsar?
Actually, we've been looking for years, and we're not alone. Each time we looked, we used better methods, better receiving equipment, better techniques. Slowly, perhaps too slowly, it dawned upon us that we had really to go all out, use every trick we knew, and that's what we did. We used the very best equipment we could build or lay our hands on. We used that, one of the best radio telescopes in the world. We used the best computing techniques that we could invent or steal, and we finally got one.
Increasingly, scientists in all branches of astronomy are pushing their equipment and techniques to the very limits to make more and more exciting discoveries about our unfolding universe. For radio astronomers, the way ahead seems to lie in the linking of telescopes as far apart as Parkes in Australia and Jodrell Bank in England to increase the accuracy of the observations. But for optical astronomers, the Earth's atmosphere is the limiting factor, and there's even an answer to that.
8, 7, 6, 5, 4. We've gone for main engine start. We have main engine start. America's first space shuttle, and the shuttle has cleared the tower.
The plan is to use the shuttle to launch a space telescope, a 94-inch reflector.
The Space Telescope, of which we've got a model here in the shuttle bay, is a complete satellite observatory. In other words, it will be able to do in space everything that astronomers now do from larger observatories on the surface of the Earth. The great advantage is that we get rid of the atmosphere. The atmosphere smears the images of everything that we see in the sky. We get a very hazy, blurred view of the universe. With the Space Telescope, we will get a 10 times sharper picture, and converting that into terms of the improvement in distance with which we can see objects, we will see everything that we can now see in the universe, but at 10 times greater distances than we can at present. In addition, we will open up other astronomical wavebands which have never been explored before by cameras. For example, no one has ever taken ultraviolet pictures of the deep universe. Equally, there will be the possibility of doing the same in the infrared waveband.
When do you hope it's going to be launched?
It is expected it will be launched early in 1985.
So you should be in time for Halley's Comet.
This is one of the drivers behind the program.
Just about then, 1985, we'll be looking forward also to the next Voyager 2 pass. Remember, Voyager 2 is, at this moment, moving out from Saturn toward the next giant planet, Uranus. It shall make its pass in January 1986 and send back the first close-range views of that strange green world with its thin rings, discovered as recently as 1977, and its strange axial tilt. Then on to Neptune in August 1989. A Neptune satellite, Triton, leaving only Pluto not contacted. We began our programme at the Royal Greenwich Observatory, Herstmonceux, still the headquarters of British astronomy, and it seems only right to end here. I hope you've enjoyed our journey. It's taken us round the world in our pursuit of knowledge. Today, we are probing out to the depths of the universe, and every year we are solving new problems, though each problem we solve seems to raise a whole host of others. I can't tell you what's going to happen during the next 25 years. Will there be bases on the moon? Can we find out once and for all whether the quasars really are immensely remote? And is there the slightest chance of our proving the existence of life on another world? I don't know. But one thing I can promise you. If I'm still alive in 25 years' time, in 2007, and if I'm still broadcasting, I'll still find plenty to say. Good night.